Hello everyone. Previously we had discussed on the topic this one DFS and the BFS tree traversal algorithms, right? So now today we'll be discussing on the topic Morris traversal algorithm. Let's get into the definition part here. What does the definition part say here? Morris traversal is a tree traversal algorithm that allows us to perform in order traversal. So this is very important. What it allows us to do, it allows us to perform the in order traversal of a binary tree without using the recursion or a stack. So this is very important part, right? So what does the Morris traversal algorithm does? Morris traversal is a tree traversal algorithm that allows us to perform the in order traversal of a binary tree without using recursion or a stack. Again, I'm stressing this one, without using recursion or a stack, achieving big of one extra space. It temporarily modifies the tree structure using the threaded binary trees. So this is fine. It temporarily modifies the tree structure using the threaded binary trees, right? So let's get into the definition part. Listen to this carefully. So whatever we discussed till here, till the end, basically the same thing will be implementing in the form of algo or the code, basically, right? So by making use of the Python programming language, right? So first, normally in order traversal requires either recursion, right, or an explicit stack. So I have said this one here, will not be making use of the recursion or the stack. So basically it performs the in order traversal of the binary tree without using recursion or the stack, I have said. So normally in order traversal requires either recursion, we know this one, we have solved n number of problems, right, on the trees already, or an explicit stack, basically. But Morris traversal avoids both by creating the temporary links, right, also known as threads, from a node's predecessor, right, back to the node itself. So that's what it does, basically. What are the steps? Let's see. First, what we will do, we will start at the root node. Always we will start at the root node itself. We'll start at the root node first, just the first point, basically. Then if the current node has no left child, then we will print it and move right, right? So if the current node has no left child at all, then we will print it and move right, quite obviously. If it has a left child, then we will find its in order predecessor, right? So if it has a left child, if the left child is present, then see here, suppose if the current node, suppose any value, right? So if it has a left child, then we will find its in order predecessor, right? Right? So that's what we will be doing, basically, right? So this is fine, I believe. If predecessor right is none, we will link it to the current node and move left. See here, this point is also important. First we discussed about the left child, then we are going with a predecessor's right, basically. If the predecessor's right is none, then we will link it to the current node and move left, right? If predecessor's right is already pointing to the current node, then we will break the link, print the current node and move right. Then what we will do, we will break the link, print the current node and move right. So we will repeat until all the nodes are processed. So this way each edge is visited at most twice, giving big of n time and big of one space, right? So now let's try to implement the same thing in the form of algo, right, or this one code, basically, right? So let's try to articulate the same thing in the form of code. First, let's define the simple node structure for the binary tree. So I'll just go with here class node, right? So this is fine. First, let's get into the construction part or the initialization part. So I'll just go with init. So this has to show init. So along with the self, we need value as well. So I'll just consider val here. This is fine. So now we have to store the node value, right? So I'll just go with the val equals val. This is fine. Next, let me go with left equals, let's initialize this one to the none. So we are just going with a pointer to left child. Also we have to make use of the pointer to the right child as well. So I'll just go with self dot right here. So this one, let's assign this one to the right itself. So why, oh this one we have to assign this one to none, not right. So yep. Now let's write the function to perform the Morris traversal basically. Let's go with a def here. So this one I'll just call Morris traversal. So this is fine. Let me pass the root over here. So within the Morris traversal function, first let's go with the list to store the traversal result. So I'll just go with result equals empty array. This is fine. We have to start from the root, right? So we have to start at the root node here. See, now let's start from the root node. Basically I'll just assign the current to root. This is fine. Now let's do one thing. We have to continue until the current is none. We know this. So let me write the while loop, while of current basically. So here let's write the simple if condition when no left child is present. So this one here, if the current node has no left child, then we have to print it and move right. So for that one, let's write the simple if condition here. So this one will be if current dot left so is none. So then what we need to do, then we have to print it and this one move right. So first let's we have to visit this particular node and we have to move to the right child accordingly with the explanation, right? So I'll just go with result dot append. What we need to append? A value of the current, right? So this one will be current dot value. Yep, this was not showing, right? So this is fine. Now current, we have to move to the right child. So this one, let's assign the current to current dot right. This is fine, man. Let's do one thing now. Let's go with the else part. So now let's do one thing. Let's move on with the case 2. So if it is having the left child, if it has the left child, then we have to find its in order predecessor, right? So this one, let me assign pre to current dot left. So this is fine, man. The next part would be while pre dot right and pre dot right not equal to current. So then what we need to do, so let's assign pre to pre dot right. So this is fine, I believe, right? So let's do one thing now. Let's move on with the further steps, right? So we have to make a temporary link from the predecessors to the current. So this one, just give me a second here. So if predecessors right is none, then we have to link it to the current node and move left, right? So else we have done that one, moving to the left child basically, right? So this one, why did I write right here? Well, pre dot right, just give me a second here. Oh, this one, yeah, let's move on with the further step. This is correct. This is fine. I got confused here completely. So this is fine. Let's do one thing. So this step, we have to move to the left, right? So this one, if pre dot right is none, then what we need to do? So then we have to make a temporary link from the predecessor to the current. So this one will be pre dot right. So let's assign this one to the current. This is fine. Also let me assign current to the current dot left. This is also fine, man. Now let's do one thing. Let's move on with the else here. So this one, if the link already exists, then we have to remove it and visit the current. So I'll just go with pre dot right here. Let me assign this one to the none. Also let's go with result dot append. So this is fine. Current dot value. So this is also fine. Finally let me assign the current to current dot right. This is fine, I believe, right? So this one we have completed. All we have to do is so we have to repeat until all nodes are processed. This is fine. So let's return the result, right? Let's return the result. This is fine. We are done with the algorithm part, right? So let's go with the example usage, man. So I'll just give here if name, let me consider here main, man. But in the strings, just give me a second here. Yep, we are going with the if condition, right? So let's go with the construction of the tree. So I'll just consider here root, let me go with node 1, and root dot left, let me go with node of 2. So let me consider until 5 or 6. Let me consider until 5. This will be fine. So this one will be root dot right. Let's consider the right child. So this one will be node of 3. This is fine. So this one has to be capital N. Yep. Let me copy the same thing here. Let me paste it over here. This one twice instead of the right. So this one will be left dot left, right? So this one will be node of 4, and finally left dot right. So this one until 5 it's fine, I believe. This one has to be left dot right. This is fine. So this one will be 5 basically, right? So basically if I try to represent this one in the form of tree, let me show you the construction of the tree, whatever the example we have considered, right? So this one I have considered the simple one. 2 left, root dot left, root dot right, we have considered node 3, root dot left we have considered 4, and root dot left dot right we have considered 5. So this is fine. Now we have to perform the Morris traversal, right? So I'll just do one thing. Let me delete this one entirely. This one, just give me a second here. So now let's perform the Morris traversal as I've said. So I'll just give here output equals, let me call the function here Morris traversal, right? So this is fine. We have to start from the root node. Let me pass the root here. Also let's print something for the interactive purpose. So I'll just go with here. So this basically performs the in order traversal itself, right? So I'll just go with in order traversal. So this one, let me call output here. Output, let me pass the output, sorry. This is fine. Now we are done with the algorithm. Basically we are done with the algorithm part. So the output that we need to get here is, so basically we are performing the in order traversal, right? So the construction I have already showed you here. Sorry, this one, just give me a second here. 1 2 3, we have considered simple example. Basically we'll be performing the in order traversal by not making use of the stack or the recursion, right? So this one, this is the main thing we'll be making use of the Morris traversal basically, right? So without making without using the recursion or the stack basically. So if you perform this one in order traversal, so this one has to be 4 to 5 first, this part, right? So 4, this part, 2 and 5 first, then followed by 1 3, this part, right? So 1 3 basically, right? So we are performing the in order traversal. This one is fine. Left, root and right, right? So this is fine. Let me delete this one. The output that we need to get here is 4 2 5 1 3, right? So let me do one thing. Let me run the code. Let me copy the file name first, right? So this is fine. Let me give Control J here, Python file name. So we are getting the error. None type object has no attribute left. This one, line number 49, none. What I have done here, if pre dot write is none I have given, so this is correct itself, right? Else I have written initially pre dot write is none. What's wrong here? I don't understand. Just give me a second here. Oh yeah, man, this is actually the indentation problem, I think. So this one, pre-dot-write, this one, whatever we have written, this one has to be within the while, right? So this one we have written here itself within the else basically. This else also I have to move, I think. Let me give tab here. This is fine. So now what happened with this one? Expected indented block and oh, this one also I have to move within this one, right? So just give me a second here. This is fine. This is also fine. This is fine. Uh, this is also fine. This is also fine. Right, so let's do one thing. Yep, we are done with this part. Let me format the document once. Let me run this one again, man. Yeah, we are getting the correct output. Basically this was the problem, indentation problem, right? So yep, this is fine. Now this is working correctly, right? So we have got the output 42513, which is absolutely correct. We are getting the desired output, right? So it performs in order traversal basically, right? So in order traversal we are getting 42513, which is absolutely correct. So 4 is the leftmost node. So basically I have already showed, again I'm telling you, just so that we don't forget this one, right? So I have considered the simple tree here, binary tree basically. So this one 4 and this one 5, right? So here again I am telling this 4 is the leftmost node that is visited first, as it is in order traversal this part, right? So 2 is nothing but here, after finishing the left subtree we have to visit the root of the subtree in order traversal, right? So this one, right? So now 5 is the right child of the 2, so we will be going this side, right, in order. So then after the left subtree, then we have to visit the root main one, so this one, right? So this is fine. Now finally we will visit the right child of the root, right? We are in order traversal, right? So this is fine, I believe. Let me remove this one. So basically this matches the in order traversal, left, root and right, right? Again in order traversal follows the this one, follows the path this one, basically left, root. Let me give here. So this one I had to write this one first itself. Now I am explaining. This is fine, left, root and finally right, this one. This is fine. Yep, we have got the desired output, right? So we are done with the Morris traversal algo basically, right? So let me summarize whatever we have learned so far, right? So just try to remember these 2 or 3 points, man. This is very important. Basically Morris traversal, what it does, it performs the in order traversal n big of n time and big of 1 space. This one we have already discussed already. So we have already discussed this one, right? See here, right? So this is fine. Morris traversal performs in order traversal n big of n time and big of 1 space, meaning big of n time complexity and the big of 1 space complexity, right? It avoids the recursion and the stacks. I had stressed this one multiple times. This is important, right? So it avoids recursion and stacks by temporarily modifying the tree links, right? So this is efficient when the memory is critical, right? So this is efficient when the memory is critical, though it slightly complicates the implementation, right? So this is efficient when memory is critical. Again when the memory optimization is required, right? So when the when we have to go with the extreme optimization, in that case going with this algorithm makes sense actually, right? So to avoid the MLE basically. By efficient, this is efficient when memory is critical, though it slightly complicates the implementation, right? This is quite complicated, Morris traversal. I'm not gonna say no. Implementation is quite complicated, but this we have to use whenever we have to go with the extreme optimization, right? I hope this part is completely clear, man. So this is it for the Morris traversal algorithm, right? So we are done with this part. Next we'll be discussing on the this one, diameter of the tree, diameter of the binary tree basically, or diameter of the tree algo basically, right? So for now this is it. Thanks for watching, guys.